Okay, so what we're going to talk about today, we're just going to do the first half of this, which involves concavity. We'll save the second derivative test for Monday, because it will be a little confusing. Concavity has to do with the shape of the graph. You've done concavity before, you just didn't know it. For instance, when we talked about parabolas, or when you have talked about parabolas, you always talk about, well, does that parabola open up or does it open down? Right? Yes? How do you determine that, by the way? Okay, good. The sign on the leading coefficient. So if it's x squared, it's going to open up. And if it's negative x squared, it's going to open down. That opening up and opening down describes something called concavity. It's the general shape of the curve. What we're going to do with concavity, though, is when you dealt with parabolas, the whole parabola was either concave down or concave up. And I'll show you what that looks like in a second. We're going to look at little chunks of the graph and see if I just look at this piece of the graph from 1 to 4, is that part of the graph concave up or concave down? And depending on the graph that we look at, it's going to change back and forth between concave up and concave down. So that's the gist of what we're going to do today. We're going to talk about concavity, concave up, concave down. We're going to talk about something called the point of inflection. On Monday, we'll do the second derivative test. And then, of course, you should be able to roll your tongue. I, however, cannot. You can't either. Anybody else not able to? Not roll like speaking Spanish.
I can't physically roll it?
Yeah, like make a U. like that. Yeah, I can't do it. They claim it's genetic. Okay, so here's the fancy the calculus speak, and I want to go through this because it introduces a concept that's going to come up a lot later on. If the function is concave up, then f is increasing. So let's just look at that statement, f is increasing. Sorry, f prime is increasing. But instead of looking at that, let's look at this statement. How do I determine if f is increasing? You just did this for the last 2 days. Elliot?
First derivative test.
Keep going.
Plug in the critical numbers.
Well, first you got to find the critical numbers, right?
Yeah.
How do you find the critical numbers?
You set the derivative equal to 0.
Okay?
Factor it.
And then test some regions, do all that other gunk. Okay? However, what's important out of that is the fact that you take the derivative and set it equal to 0. Then we find the critical numbers, then we test regions, blah, 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 blah. How would I figure out where f prime is increasing? Take the derivative. What's the derivative of f prime? F double prime. And set that equal to 0. Find the critical numbers, test regions, blah, 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 blah. So that's the fancy definition of concavity. What we're going to use more frequently is this definition. Even though they call it a test for concavity, this to me makes more sense. If the second derivative is positive, then it's increasing. If the second derivative is negative, it's decreasing. We're doing the exact same thing we did with f and f prime, but now we're doing it with f prime and f double prime. And it's giving us different information. That information is concavity, which I'll go back in a second and show you what the pictures look like. But I think you probably have a pretty good idea already. Okay, does that make sense so far? Good. Here is what concave up looks like. It's like an upward opening parabola, like a bowl, something that would hold water. Concave down, however, is an upside down bowl, something that wouldn't hold water. And you can see we can put those pieces together to build more complicated graphs, where part of the graph will face up and part of it will face down. Your job initially is going to be to figure out where that happens. Where is it concave up and where is it concave down? Okay? Questions so far? Good. Then do it. We're going to start slow, and then it's going to ramp up pretty quick. Derivative number then?
Wait, is this? Wait a second. Yeah. This is a first derivative. First.
It's just like when you're testing regions to figure out where it's positive. So remember, when we took the derivative, then we tested the regions for positive and negative, where it's positive is increasing, where it's negative is decreasing. We're gonna tweak that a little bit. I purposely wanted him to slap that up there and then fix it, make it a little clearer. Okay, so it appears what Christian did was he took the first derivative, didn't do anything with it except take the second derivative because we don't care about increasing and decreasing our maxes and mins right now. Set that equal to 0, found the critical number. Then you put it on a second derivative number line. Is that what you got going on there, Slim?
Yeah.
Good. I'm going to tweak one small thing. Because we don't want this to get confused with what we did with the first derivative, we're going to get rid of the arrows. And we're going to turn those arrows into concave down and concave up. CD and CU. Okay, so we've got a graph from negative infinity. It's always concave down. Then it hits a point. That point is negative 1/3. And it flips over. So it would look something like this. Concave down, got an upside down bowl. Then it gets to negative 1/3 and flips over to a regular bowl. Does that graph make sense with what you know about that? Yeah. Does that look like a cubic? Yep. This point right here, where it switches, is called a point of inflection, abbreviated POI. A point of inflection is just like a max or a min, except it does something different. It's a change in positive to negative or negative to positive, and it causes a change in concavity. So it either goes from concave down to concave up and concave up to concave down. Now, the nice thing about points of inflection is there aren't two different kinds. It just, if it changes, we have a point of inflection. Okay, unlike the maxes and mins where you got to go and test to see if it's a max or a min. This is just point of inflection is a point of inflection. Anytime the second derivative changes sign, you get a point of inflection. Does that make sense? Any questions? Okay, good. Let's do something a little more challenging. Oh, here's all, I did the work too, but it's just exactly what Christian did. I don't know why I took the first, yeah, blah, 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 blah. And then there's my second derivative number line right there, and I put on 1/3, and then again, okay, great. Try that one. Is everybody doing quotient rule, or did anybody do product rule? Quotient. Anybody product rule? Just checking. Okay, that's cool. I mean, you don't have to. Fine. Remember, don't multiply out denominators. It should be fun. Your answer is right there. You should just remind them because there's two
times 6.
I looked at, I think I would GCF.
Let me have multi-class.
Yeah, to the extent that you take 2 times 2x times maybe 4. Once you get to that point, factor out a GCF and then
Real quick, before things get ugly, do you all agree?
Yes.
Okay, we're good there.
Yeah.
Carry on.
not everybody. Well, I'm not sure. Oh, wait, no, yeah. Does it though? Yeah, no. This becomes 2, this becomes 4. No, this becomes 1. This becomes 4.
Oh my god.
That's irrelevant. That can't generate a negative number. That can't generate a negative number, so there is no critical number for that.
If this was minus 3, also a critical number. Since it's not solvable, then we don't worry about it. It's irrelevant. It doesn't do it. I mean, because then we'd have to go into the imaginary numbers in order to get and we don't want to go over. So you should get some critical numbers on the numerator, though, right? Yeah. You'll see why. I'll do the derivative, then you'll see why that's not advantageous. You got critical numbers? Okay.
No.
Hey, Armin.
Why did you say
You're right there. Okay, so just to make sure we're all on the same page, I'm going to go and do the second derivative, but before I do that, let's talk about that first derivative there. Where are the critical numbers for that first derivative? 0 and?
That's it.
That's it. Why, Tom?
Because there's no critical number for x and y.
Good. Remember, we don't deal with imaginary numbers. In order for that bottom to be 0, you'd have to have the square root of -3, which doesn't work for us. Okay? So, that having been said, let's move on to the second derivative. Walking around the room, most of you found the second derivative just fine, but it's the simplifying that was causing problems and making your life difficult. So, I'm going to go through it step by step and give you some points that might make your life a little bit easier. Okay, so quotient rule, x squared plus 3 to the 4th power. Bring this up on top. Okay, do we all agree?
Yeah.
Okay. I'm going to clean it up a little bit, but not too much. Now, here's where some of you went down a dark path. Some of you decided, I'm going to multiply out that numerator. Oof. Yeah. It's possible, but what happens is you end up with a quartic, and that gets a little hairy. So I'm going to show you a different approach, and that is, once you have this multiplied out with as a summation, then factor out a GCF. So the GCF there would be, I'm going to do -12 and x squared plus 3. Now I have to decide to what power. Remember, you always take the more negative power, so I'm just going to take out one of those. What am I left? What do I leave behind? Well, I took out the -2. I left an x squared plus 3 behind from the first term. That takes care of that one. And I leave a 4x plus 4x squared, and that other thing disappeared. Like we talked about in the first derivative, the denominator is irrelevant. It doesn't affect us at all. This term is irrelevant. Can't be equal to 0. So all I need to worry about after this, wait a second, this should be a minus, sorry. The only thing I have to worry about now is that puppy. In other words, -3x squared plus 3. Did I do my math right? Somebody help me out. Julia, did you have a quadratic in there, or did you get the same thing I had?
Me? I had x squared minus 4x plus 3 as my quadratic.
X squared minus 4x squared plus 3.
No, x squared minus 4x plus 3.
Oh, that's because I made a mistake. I took an x out of there. Didn't I? No, I didn't. Okay, did I screw up? No, I'm good. Okay, so let me go through this again. I got to this point, and I have two terms here. Here's one, here's the other. And I looked at the GCF between those two terms. The GCF between those two terms is, I chose to take out the negative, so I got negative 12 times x squared plus 3. And as we've talked about all along, you take the smaller exponent, so I took out just one of them. So this, when I took this expression out of the first term, it left an x squared plus 3 behind. That took care of that. When I take out of this, I'm going to have a minus sign now. 12 into 48x squared is 4x squared. This whole thing is gone in front, so it just left me with a 4x squared. So it should be a squared term. Yeah. X squared minus 4x squared is negative 3x squared. And then I got a plus 3 sitting there, so that makes it plus or minus 1. So after all that work, what I just found out is that my critical numbers are something nice and pretty like plus or minus 1. Oh, good question. Why don't I use the stuff I took out? For the same reason I didn't use it over here, because it can never be equal to 0 without using imaginary numbers. Right? So if I take this, this is an F double prime number line, so I'm plugging back into F double prime. If I put in negative 10, I'm going to get a positive answer and a negative answer, so this will be negative. It's concave down. If I put in 0, I get positive, positive, so this will be positive, concave up. And if I put in 10, I will get concave down. All right, so Monday, we'll pick up where we left off and talk about something called the second derivative test.